Hello everyone, welcome to chapter 15, Kinetics of a Particle, Impulse and Momentum. In this module we are going to discuss angular momentum as well as the relation between moment of a force and the angular momentum. Also we are going to discuss the principle of angular impulse and momentum. So, objectives are first to determine the angular momentum of a particle. What do we mean by angular momentum and how can I find it? And then we are going to apply the principle of angular impulse and momentum. Also, we are going to use conservation of angular momentum to solve different problems. So first of all, to define what is angular momentum, the angular momentum of a particle about a point O, as shown in the figure to the right, is defined as the moment of the particle's linear momentum about O. Meaning, what is my linear momentum for this particle P, the one that you see in this figure? Okay, so this is my particle, and it has a linear momentum mv. If you take the perpendicular distance between that momentum, linear momentum, and the point that I'm discussing or I'm referring to, point O in this case, then mv times the distance is called angular momentum. It's like when you have a moment of a force. You have the force multiplied by the perpendicular distance between the force and a certain point. So H is the letter, capital H is the letter that we use for angular momentum. So capital H around point O, so it's around point O, and I have to decide which axis. I'm doing it for the Z axis. So HO around Z axis equals to the distance D multiplied by the linear momentum mv. And the units, as you can guess from the parameters, you have kilogram meter square per second or slug feet square per second. And for directions, we use the right hand rule for directions. Now, the form that we've seen here, this is a scalar format that we have here. This is a scalar way of calculating it. If you have it in a 3D problem and you want to do it in a vector format, then HO equals to R cross MV, and you have to do it properly, that meaning that you start with R cross MV. So you have IJK, three components of R, Rx, Ry, Rz, and three components of linear momentum, MVx, MVy, MVz. Okay. Now, to see the relation between the moment of a force and the angular momentum, the resultant force acting on a particle is equal to the time rate change of the particle's linear momentum. Meaning, we know that from Newton's second law that summation of forces equals to ma. Okay, I can write A as, so I can write this as m, okay, and I can write this as d dt of v. Now, mv is a linear momentum. M times v is my linear momentum. Now, the problem says that the resultant force acting on a particle, which is this one, is equal to the time rate of change. What does time rate of change mean? This means time rate of change means d dt of something. Time rate of change, time, d dt. It is equal to the time rate of change of the linear momentum, and you can see it. It's mass times velocity, and I have the time rate of change. So instead of A, I'm going to call it v dot. Okay, so I'm going to call it as v dot. Okay, so this is clear now how we came up with this definition. Okay, now, since summation of forces equals to mv dot, remember that the linear momentum mv, we used to call it L, so mv dot, I'm going to call it, in this expression, L dot. So summation of forces equals to L dot. Now, the next point to come up with the principle of angular impulse and momentum. Now, we can prove, and we are going to do this now, that the resultant moment, okay, the summation of the moments acting on a particle about point O is equal to the time rate of change. Remember that time rate of change means d dt of the particle's angular momentum about point O. So I want to prove that the same thing that I did here, I can do it for angular momentum. So let's do it. Summation of moment equals to R cross summation of forces. Force times perpendicular distance R will give me moment, so I'm just adding the summation in here. So summation of moments equals R cross summation of forces. And what do we call the summation of forces? L dot. So I'm going to use this. And what is L dot? It is mv dot. So I'm going to write it as R cross mv dot. Now let's leave this on the side. We want to prove that this resultant moment is equal to the time rate of change of the particle's angular momentum. So angular momentum h equals to R cross mv. So h should equal to R cross mv. But we're saying we want to make sure that the summation of the moments should equal to the time rate of change, d dt. So I'm going to add the dot in here. Okay, so h dot around O should equal to the time rate of change, d dt of R cross mv. Now from mathematics, you know that you're going to say dr dt, which is R dot cross mv, and this equals to 0 because R does not change with time. The distance R should always be the same, it's a constant, so it does not change. Plus R cross mv dot. So now you can see that from here, R cross mv dot equals to summation of moments, and here R cross mv dot equals to h dot O. Therefore, this is what I needed to find, that these two are the same, are equal. So now I'm going to open this, and this is the final step, bear with me. The final step, and this is where we end. Let me write this as d dt of HO. Now I can take this dt to the left hand side and then integrate both sides. So that's what we do. Summation of moment equals h dot O, which equals to d dt HO. Take it to the other side, as we said, the dt, you end up with this principle. Taking HO1 to the other side, which is similar to the principle of impulse and momentum, except that it is angular instead of linear. We used to have mv in here and here, now we have mv times r. We used to have summation of integral of forces dt, now we have moments instead of forces. And this is what we call angular impulse. Okay, that's basically the theory. So as a summary, the principle of angular impulse and momentum says that R times m times v1 plus summation of the integral of either you have moments or you have forces multiplied by the distance, which will give me a moment effect, dt equals to R mv2. Now for a system of particles, all you have to do is we do the summation in here and there. Now one important point is that I can use this in some problems with the principle of linear impulse and momentum. Now to have the two theories side by side to compare them, this is in vector format. So I have the two are the same. Here you have the linear momentums and the impulses, and here you have angular momentum and angular impulses. In scalar format, usually, let's say if you have a problem where the particle is confined to move in a plane, meaning that its linear motion is happening in the plane xy, whereas the angular momentum is happening in the perpendicular axis, which is the z-axis, then you have these three equations: 2 linear impulse and momentum, and 1 for angular impulse and momentum. Finally, the last point to discuss is the conservation of angular momentum. Exactly the same way we dealt with the linear impulse and momentum, when the sum of angular impulses, okay, acting on a particle or a system of particles is 0, during the time from t1 to t2, then the angular momentum is conserved. So I could have cases where I have no forces, and this is, or no moments, or I could have moments that are opposite in direction but equal in magnitude and they cancel. In this case, I end up with the conservation of momentum, no impulses. Rmv1 should equal to Rmv2, or I could have a system of particles where I have the summation of HO1 equals the summation of HO2. Now, let's start with the first example. The spheres A and B, each weighing 4 pounds, are welded to the light rods that are rigidly connected to a shaft as shown in the figure. If the shaft is subjected to a couple moment, m equals 4t squared plus 2 pound-feet, where t is in seconds, determine the speed of A and B when t equals 3 seconds. The system starts from rest and neglect the size of the spheres. So I'm dealing with them as particles. Now, to look at this problem, what forces do I have? I have the moment that is applied here. I have the weight of B and A. And what else? They are welded to the rods, so there's nothing in there. Now, you might have some maybe these are welded, so they are not actually moving, so you don't get any moment in here. Okay, and that's it. That's the only forces that you have. So first of all, you start with drawing the free body diagram of your problem. Okay, so I'm going to consider this one with the rod and the spheres as well. Okay, so all of this are welded together as written in the problem. So this is my system. So if I'm gonna draw this, I'm gonna have, this is the collar, and then I have two spheres that are identical. So everything is identical in this problem. So I have the weight, okay, and I also have, this is my vertical axis, okay, so I also have the moment that is applied, which equals to 4t squared plus 2. And what else do I have? Now I have to put the distances and the angles. This is 45 degrees. What else do we have? Let's look at the distances. This is given as 2.5 feet. So I can find these distances easily. I can say that I will need obviously this distance because this will give me the moment. So this equals to 2.5, okay, cosine 45, or sine, doesn't matter, it's the same thing. And this is the same basically. Okay, so these are the forces that I have in this problem. Okay, now let's start with the principle of angular impulse and momentum. So what do I have? I have H1 around the z-axis plus summation integral over time of m around the z-axis. Sorry. So I'm taking the integral of m around the z-axis. Okay, dt. This should equal to h2 around the z-axis, the same thing. So this will give me, originally at rest, there was no movement, it was 0, plus, now, I have the moment that is applied, so I have integral from 0 to 3, because it is done over 3 seconds of the function for t squared plus 2 dt. And then go back to the problem. Let's see, the weight actually here does not give me any moment around the z-axis or the vertical axis in this problem. So we are calling this axis z-axis in this case. So they are not giving me, they are parallel to it, so they don't give me any moment in this case. So that's the only force that I have. Now this should equal to, since the two spheres are identical, I'm going to say 2, okay? And then I have the mass, so the weight is 4, and in British system units the weight is 4 pounds. To make it mass you divide by 32.2, 4m. Now velocity is unknown, I need to find the velocity. Keep in mind that, look at this problem, because of this moment that is rotating, these two will start rotating, the two balls will start rotating around the z-axis. So the velocity is coming outside of the page or inside the page. So you cannot see it in this 2D plane, but the velocity is coming out, and therefore it gives you an angular momentum around the z-axis. Okay? For example, if you think about it, that these are my axes, let's say this is x, this is z, and this is y, so they are coming in the y-axis. Okay, so this is the velocity, so they are similar to this axis, the z-axis, coming outside of the page. So these velocities, I'm going to write it as v, so this is m times v times r. Remember that the angular momentum is r times m times v, or m times v times r. So this is the mass, this is the velocity. Now what is r? It's basically this distance. So it is 2.5 cosine 45. So v multiplied by 2.5 cosine 45 degrees. Okay, carry out the calculations, you end up with 4t cubed over 3 plus 2t, okay, and these are, these are between 0 and 3, the integral. So basically you have to apply these at t equals to 3, okay, and this should equal to, the other side will give you 0.4392v. If you apply the t at 3 seconds, which was given in the problem, this will give you that the velocity should equal to 95.6 feet per second. Okay, and this solves the first problem, just to show you how to apply the principle of impulse and momentum. Now let's look at another example. The 10-pound block rests on a surface for which mu k equals 0.5. It is acted upon by a radial force of 2 pounds, okay, shown in the figure here, and a horizontal force of 7 pounds, which is shown in here. Always directed at 30 degrees. So this 7 pounds is directed at 30 degrees with the tangent line. So whatever tangent is here, in that case, you get 30 degrees with that tangent to the path always. If the block is initially moving in a circular path with a speed of 2 feet per second, at the instant the forces are applied, find the time required before the tension in the cord AB that connects B to A becomes 20 pounds. Neglect the size of the block for the calculation. So the first thing we want to do here is that let's start with the free body diagram. Okay, so this is kind of a 3D problem, so I have to draw a 3D drawing of my block in this case. So it's gonna be something like this. Okay, so always I need to put all the forces acting on my system, and then from there I can understand what I have. So first of all, I have the 2 pounds coming out. Okay. Okay. I have the tension. Remember that we want to solve for the case where the tension will equal to 20 pounds. That's when the problem asks you to solve. I have the weight acting downward, and the weight in this problem equals to 10 pounds of the block. What else I have? I have the horizontal force. If this is the tangent at this point, so this force equals to 7 pounds, and it has an angle of 30 degrees. And also I have a normal force. Okay, this is the normal force. And finally, if this is going to move on the surface and it's not smooth, then I'm going to have friction. Now, where is the friction going to be? If this is moving along this curved line, at this point it's going to be opposite to motion, tangent to the path, so it's going to be acting in this direction. So I'm going to have mu times n. So in this case it's going to be 0.5 times the normal force. So it's going to be in this direction. Okay, friction force that equals to mu k times n. Okay, now to solve the problem, what is asked for me to find is find the time required before the tension in the cord becomes 20 pounds. Now, if I go to the principle of angular momentum, keep in mind that I do not have an information about the final velocity. I only know the initial velocity, what's it going to be, which is the one that is given to me in the problem as 2 feet per second. So therefore, I need to find the final velocity first. The final velocity occurs when the tension becomes 20 pounds. Find the time required for the tension to become 20 pounds. So I need to find the velocity at that instant. So I can do Newton's second law in this case, and I can do summation of forces. And let's say if this is the normal direction, and this is the tangent direction, normal and tangent, so I can do summation. If this is positive, summation of forces in normal should equal to MAN. Okay, so what I have the in the normal direction, I'm going to have the minus 20. Okay, or sorry, since the normal acceleration is going to be in this direction, and always towards the center of the curve, the acceleration, I'm going to have that one as my positive. Doesn't matter, it's just I like to make it more organized. So it's always AN is positive in the direction of the direction towards the center of the curve, which in this case is point A. So I'm gonna do it in this direction. So I have 20 pounds minus this 7 pounds will give you a component, so it's going to be minus 7 sine 30 degrees should equal to the mass, which is 10, the weight, divided by 32.2 multiplied by AN. Now AN, if you remember from kinematics, equals to V square over rho. So it's going to be multiplied by V square over rho, and rho in this case equals to 4 feet. So it's going to be V square over 4. Everything is known in this except the velocity, so this will give me that the velocity should equal to 13.67 feet per second. Now I can apply the principle of angular impulse and momentum. H at point A, okay, 1 plus summation of the integral of m dt should equal to h around A2. Now HA1, I know the mass is going to be 10 divided by 32.2, so m times velocity, which is 2, times the distance or the perpendicular distance, which is 4, in this case r, so mvr, plus, now weight does not give me a moment around A, normal force does not give me, The 2 pounds does not give me. The 20 pounds does not give me. So I end up with the applied 7 pounds and the friction force. Those two are the one that will give me an angular impulse around point A. So let's start with the 7 pound right hand rule. So upward is going to be positive. Then I'm going to have plus, the force is 7 multiplied by its component, which is cosine 30 degrees. So this is the F. I need to multiply it by R to make it a moment, which is 4. And don't forget, many students do this, believe me, they forget to multiply by the time. Multiplied by the time. Okay? Then friction is opposite to the motion, so it's minus friction coefficient 0.5 multiplied by the normal force, which equal to the weight in this example. So 0.5 multiplied by 10. This is the force. Multiplied by the distance to make it a moment, which is 4. Multiply it by the time, which is t. This should equal to the HA2 should be similar to HA1 except for the velocity. So it's going to be 10 over 32.2 multiplied by the velocity, which is 13.67 multiplied by R, which is 4. So everything is known in this problem except for the time. Applying this one here gives you that time should equal to 3.41 seconds. So as you can see, and we've done this in previous modules as well, whenever we discuss principle of work and energy, principle of conservation of energy, or even principles of impulse and momentum, or angular impulse and momentum, always sometimes you might go back to either kinematics or Newton's second law, as we did in here, to solve part of the problem. Sometimes some of the unknowns you should do an extra step before or after to find them. So always when you want to solve these problems for these chapters, just keep your mind open to everything that you've studied or everything you know in dynamics, as some of these problems, and probably a large part of these problems, will require you to use different concepts in order to come up with the solution. And this, I conclude this module. I hope that it was useful to you, and I wish you the best with your studies. Thank you all.